for 2 years. And you also want to capture the new vessels. Now, the thing is that ship operators have got different numbers of ships. And this is a competition to capture ship operators. That's basically the battle that we're in. So let me take you through the diagrammatic analysis that we did of this problem. I do hope this works. We love Skype, it just interrupts everything you do. I've now sent it away, I hope. Okay, so this is the stock of ships that have got our ballast water treatment system in it. BWTS is ballast water treatment system, okay? So if we want that number to grow, we have got to install our ballast water treatment systems at a rate that is good enough to build what we want. So what might that rate be? We are one of 50 competitors, so the average competitor might grow this to about 1,000. We want to be better than the average competitor, so we might want this number to grow to 3,000. Now, that's not going to happen instantly. This is going to happen over a number of years. So let's say that's going to happen over 3 years. That means that this number here has got to average 1,000 per year. Have I got that right? Okay. So I need to install this thing at the rate of 1,000 per year. Now, to do that, I have to have installers. And I'm not going to spend time on what has to happen to the number of installers in order to hit that installation rate. But this is an important part of the question. Installers have to be happy installing my solution because they have to satisfy the ship owners who want their ships converted. So where do those ships come from? Well, they come from a stock of our potential ships. So initially that's going to be none because we haven't sold to any ship owners. We hope that there are going to be lots of ship owners signing up with us so that we can install those systems and move them over here. So if I had 1,000 ships signed up, I could now start on this process of installing 1,000 ships. If I had 3,000 ships, I could start installing 3,000. The difficulty is ships don't make decisions. Ship owners make decisions. So what I need is, I need to do some things first. Let me give myself some space. What I need is I need ship I'm calling them our ship owners. This is the owners who have agreed to install my treatment system and not somebody else's. And when I win one of these, so that is one ship owner I've won, that ship owner brings with them however many vessels they have. So how many ships do they have? So let's say the first ship owner I sign up brings 50 ships per owner. So I've agreed with one ship owner that I'm going to install my ballast water system in his ships. He's got 50, so I can start on the process of installing 50 systems. So that has now gone plus 50. That's gone from here to there, so there's my 50 number. And I'm going to start on that installation process, so that's going to go down. So I've won one ship owner, and now I'm going to win another ship owner and another ship owner. And each of those is going to bring 50 ships, so this increases, but then I start installing them and that goes away. So the next question to ask is, why does a ship owner agree to install my system and not somebody else's? And that's basically to do with our system performance and the price. And these systems cost something like 100,000 euros per system. So if I take that number and that number, that is my revenue. So if I initially start at the rate of 10 systems per month, then I'm going to make €1 million per month. I've obviously got to get a much bigger number than that in order to win in this market against the other 49 competitors. So here's the thing. There is somewhere else the ship owners could go, which is that they could become rivals customers. And over here is ship owners not installing. So this number is gradually going down. This number is going up, and we have got some ship owners. The thing that's going to change is that we are within 5% of the voting members on the International Maritime Board mandating that you have to install these systems. So this rate is coming down quite slowly because it's almost voluntary at the moment. The time is going to come when this adoption rate here, which is quite slow, has to be fast because these ship owners will be under pressure from the regulation that you've got to install these systems, and you've got to install it by 24 months from now or 36 months from now. There will be a window of time to install these systems. So that's the architecture of the system that we are trying to populate with information. And what's the information we need? We need to know how many ship owners there are out there. We need to know how many ships each of those has got. We need to know what our system performance is. We need to know what rivals' performance is. We need to know what the system performance does to the ship owner's decision to go with our system and not your system. And there are lots of different issues there. There's how easy is, how well does it clean the water? There is how reliable is it? how easy is it to maintain, how costly is it to operate. So this performance thing is actually 5 or 6 major issues that you have to satisfy the customer about. Now, if we're successful in this, what happens is that this number here, the ships that are installing our system, everyone knows that it's our system that's being installed, and that drives this decision by other ship operators to choose our system instead of somebody else's. So there's one of our nice reinforcing feedback things. And this little thing here is a balancing feedback. I've got to keep winning more customers so that I've got more ships that I can install my system to. And on top of that, we have got some very interesting cost and performance dynamics. So the unit cost of producing this system is currently some number, let's say, around 100,000 euros. That unit cost we would expect to come down because there's a very well-known phenomenon in manufacturing known as experience curve. And what the experience curve does is it says every time this number, the production rate doubles, every time the production rate cumulatively doubles, this cost will come down by something like 15 to 20%. Okay, so to produce the first 10 cost me 100,000 euros. To produce the next 10 cost me 80,000 euros. To produce the next 20 cost me 65,000 euros. To produce the next 20 cost me 50. You see what's happening? The more we grow, the more the unit cost comes down. And what that means is that we can reduce the price, which means that more ship owners adopt our system. Okay? So that's just a picture of how the process I described this morning actually starts. This is a discussion I had online with the managing director of this company 2 weeks ago, and he is very keen to actually, he wants to build it himself. He wants to build the working model of this case himself so that he can make decisions about pricing, about capacity expansion, about sales effort, about how many installation engineers he needs, about which ship owners to go for, which sizes of ship to target. Should I go for big ships, medium ships, small ships? There's a lot of choices he has to make, and this is going to help him make it.
Thank you. Thank you very much, Kim. I would kindly ask for just a couple of questions because we need also some time to change the relators. So, are there any questions?
Yeah, I think one curiosity. Aren't there any other productions in departments, like departments of scale?
Yes, there are. Yeah. The question, in case you didn't hear, is are there not other cost reduction factors going on here? Economies of scale is clearly one of those. You know, unit costs come down if we produce more, even with the same experience. So yes, for sure. And there will be cost economies in installation as well. It'll cost us more to install the early systems than it does the later systems because we will codify the procedure for installing the system, particularly if we target a very large class of ships. So ships come in different classes. If you design a system that is ideal for a particular class of ship, then you can have very effective installation procedures for that class, and you just clean up in that class of ships.
Okay. One more question? No? Okay. So thank you, Kim.
Okay.
We will see you back in the final session at the end of these presentations. So next presentation is from Marco Lupo. who will tell us about the system dynamics application in the pharmaceutical industry. Marco Lupo is working for Takeda Pharmaceuticals.
Good afternoon, everybody. My name is Marco Lupo, and it's a pleasure to be here and sharing my limited experience in the field, but hopefully from a different corner. And indeed, what I would like to start with is self-introduction of myself. This could seem a little bit egocentric, but I don't find myself such an interesting topic to discuss at a workshop. But I think it's important to give you a little bit the idea of where I'm coming from and the different maybe standpoint I have compared to other professionals and practitioners in the field. Basically, I've experience in the Lean and Six Sigma methodologies. How many of you are familiar with Lean Six Sigma? To give me an idea. Okay, I will just say a little bit more. So basically, my role is an internal consultant role in the company. And I came in contact first time with system dynamics when working at Johnson & Johnson, approximately in 2005. After that, I worked for MSD, or Merck Sharp & Dohme. And now I'm currently working for Takeda Pharmaceuticals. The three of them are pharmaceutical multinationals, let's say part of the big pharma companies. And basically in this internal consultant role, I've been using system dynamics as needed. So this is where I'm coming from. Basically, in the pharmaceutical industry and in my role in the company, normally I'm not asked to do any system dynamics modeling. And I'm not even asked to do any modeling and simulation. I'm typically asked to help solving an issue, solving a problem, or improving something. Hopefully, based on my background, sometimes I'm in the lucky position to propose a modeling and simulation approach, and often a system dynamics approach. Not in the majority of the cases, I have to say, but sometimes. And I have to say this is very important in the perspective of how to, let's say, present the methodology and how to gain interest from a stakeholder. That normally I don't experience a lot of interest for modeling and simulation in itself. I experience interest to gain some result, to solve an issue. And if I'm capable of explaining that system dynamics can help getting to the objective, then I can try to get acceptance for a system dynamic approach. And in this perspective, it's again very important to do the right setup in terms of level of detail and scope expected from a model, setting up the right expectations. Because making a mistake in this first phase could actually be the root cause for failure in the application. And I have experienced success and failures as well in the application of system dynamics in this environment. Very importantly, I have to say, in my experience in the industry, it is very important that building a system dynamics model is a collaborative process that brings together knowledge, mental models, we may say, from different people from different roles in the company participating to a modeling and simulation team. And this is extremely important. Sometimes the system dynamics modeler might feel the frustration and the impatience to move on and build an extremely sophisticated model, but this is not gonna work. What I've experienced is that it's only gonna work if you build a model where each person who is part of the team is actually understanding the model. Not maybe each single equation and all details about system dynamics, but understanding the logic of the model in the holistic view. This is very important, and I think if you go too far away and the team is not with you, it is gonna be a failure. It's better to have a simple model where the team is with you rather than doing any sophisticated thing that will not have the trust of the participants. This is a very important point that I want to raise, and I think also in the industry framework, the modeler skills need to be a mix of facilitating skills and modeling skills. An average modeler with good facilitating skill will probably succeed more than a fantastic modeler with poor facilitating skills. So that what I typically say when I start this type of project is, all models are wrong, but some are useful. How is this fitting with Lean and Six Sigma? Basically, Lean and Six Sigma are two methodologies with different histories, but used now in a synergic way in many companies, basically following a roadmap. And within the roadmap, providing a set of tools. And the roadmap is the following. Basically, you start defining a problem, what the problem is, what the objective is, what the scope is, and so on. Then you start measuring the problem without jumping to solutions. Based on the trustable data that you collect, you make some analysis, try to identify the root cause for the problem you are working on. Only after that, you start looking at solutions, comparing different solutions and trying to pick the optimal solution. Also trying to identify side effects of making some changes in a system, especially important in a highly regulated and ethic environment like pharmaceutical. Finally, there will be a control phase where you make sure that you have gained the improvements you wanted to gain, that they are sustainable, and you have not created any other problem by solving the problem you initially wanted to solve. System dynamics work very well in this environment. In the define phase, it helps setting the scope, what is in the project, what is out, mapping it, having the holistic picture. In the measure phase, it helps limiting the amount of data you need to collect. And in the analyze phase, it helps actually identifying the few critical variables within probably a large number of potential causes for your problem. In the improve phase, of course, that's, I guess, the most obvious application. You can run scenarios for free, we may say, identifying the optimal solution and also the side effects of your choice. And in the control phase, of course, you can make sure it's working, but as you are normally identifying a generic solution to specific problems, there is a high leverageability of the results. And a model that has been used for one issue can easily be reapplied to similar issues, or even to manage the knowledge gained in the process. So this is about the synergy. Now, I've been running a number of models in my experience. Some quite operational, for instance, simulating the fluid bed granulation process, a typical key process in tablets manufacturing, for instance. Or, for instance, I've been doing some manufacturing process optimization. More on the strategic level, I've been doing different things. For instance, a model to maximize off-patent drugs sales, or an integration change management model. Just to give you some examples. Important to say, those models were normally effective in achieving the results. Out of this big list, only in 3 or 4 cases, I have been building more or less orthodox models in terms of closed-loop diagrams and so on. Other times, I've been doing quite a simplified view. Maybe not orthodox, but probably effective for the purpose of the application. I've picked 2 examples to give you an idea, and I've not picked the most complex ones. I'm not an experienced modeler. I don't have much to share in terms of that. I've picked 2 that were relevant for the business. So maybe not very fancy from a system dynamics perspective, but important in my experience. The first one is a very operational model. We had a capsule filling process. Very simple process. There is an automated machine that is filling capsules with pellets, closing the capsule. The capsule goes through 100% weight check. And some capsules are sampled and tested in the quality control for the content of API, active principal ingredient. And in this process, we see that we have some scraps, but mainly we have the most scraps in the filling weight selection. So the weight of the filled capsule is not within the specification, and we have to scrap the capsule. If you look at this is the distribution of the filling weight in the capsule, and those are the specification limits. In this process, we only have 80% yield. Every 100 capsules we produce, we have to scrap 20. It's a big scrap. When we look at the critical quality attribute, actually assay, so the content of API, this is a perfect process, very capable. So the question is, how could we improve this? We would like to have good quality, but higher yield. And one part of the question, we can get it with traditional means. We know that there is a certain distribution of the filling weight, and we know that if we would enlarge the specification limits, we would have higher yield. Instead of the 80%, we could move the specification limit in order to get much higher yield, up to 98%. This is quite clear. This is not rocket science. The question is, if I do this change, what is the impact going to be on the assay, on the quantity of API in the capsule? So that in this very simple view, there is one question that we can assess. So what is the impact of the weight distribution on assay? This is something we can answer with traditional regression analysis. What we cannot answer with our traditional tools is how does a change of the selection limit impact the weight distribution. And this is something that we cannot answer with traditional means, but we can with system dynamics. And this is what we did in this case. So we were actually running a number of scenarios. We may say the baseline with this tight specification and an improvement scenario with wider specification, verifying that we are not increasing the risk of failing the release test, not increasing the risk of failing the assay of the capsule. So basically, we have a justification to enlarge the specification limit. What we have achieved was increasing the yield of the process by 15% without increasing the risk of failures, and also having a science-based risk assessment of the change that was instrumental to get the change done. We would have never succeeded to get such a change done in the pharmaceutical regulated environment without a solid justification. And on top of that, we have very good knowledge management. The knowledge gained in this process could be reapplied in similar ones. Very simple kind of Monte Carlo simulation, but with very good business results. Different model, a strategic model. Basically, we had a merge process, 2 companies merging, and we were looking at change management. How are the employees going to accept this big change? We refer to a non-change management model. So within a change, people will come in contact, will be aware, will understand the change, will have a positive perception, then they will experiment, adopt, and so on. And how are we going to change the position of the people in these fields? You may recognize in this model an inspiration to Mr. Warren customer loyalty model. Indeed, I learned about that in one conference and I was thinking about it. So how do we move people through this scale? There is some factors that are going to move them. Some are within our control. For instance, we can do communication. We can create some teams where we bring the people from the two former companies to work together. We can harmonize procedures and so on. There is also other things that we cannot control. For instance, when there is a merge process, there is always a lot of rumors. People talk and talk, and there is rumors that this or that is going to happen. We cannot control this. We can hardly measure this, but this is still moving the people backwards in the process. So somehow we have to capture that. And basically, this is what we did. So we tried to build this model, quite empirical. And in order to measure the baseline and to try to somehow calibrate the model, we were running surveys among employees with a number of questions that were resulting in the employee self-positioning himself in one of those stocks. And then we were trying to simulate the past and afterwards, obviously, the future, trying to help support the right decision in terms of which policies to apply to get the people through. So, not rocket science, but something that proved very useful. So in conclusion, my experience from the pharmaceutical industry is that system dynamics is great. It can be very helpful. And it's also important to have such chances to learn from academic, other fields. Should not be applied as a religion, should be applied on a practical standpoint, and the modeler should be a good facilitator with some patience to bring the team with him. Not a superhero with maybe super capabilities in terms of modeling, but leaving the team not understanding anymore what the model is about.
Thank you, Marco.